Good morning, everyone. This is the Big O notation present by Karina, Luke, and Haran. So let's get started with the history.
Big O notation was first documented by Paul Bachmann as a method for evaluating how closely a series can approximate a given function. For example, consider the Taylor series for sine of x, which is equal to x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial. In mathematics, what a series is to a function is what in computer science your algorithm is to the optimal way to sort a given list. For example, if the list is 3, 2, 1, and your algorithm is going to compare two adjacent values, it would make the following swaps. 3, 2, 1 would become 2, 3, 1, the 2 and the 3 swap, then 2, 1, 3 with 3 and 1 swapping, then 1 and 2 swap to be 1, 2, 3. However, the optimal way to sort this list was to compare the first and the last values and just make the single swap of 3, 2, 1 to 1, 2, 3. Technically, Big O notation is called Bachmann-Landau notation, to attribute a founder of Big O and a colleague of theirs, or asymptotic notation, due to its use in approximating functions. In the 1970s, Donald Knuth wrote his The Art of Computer Programming. This is literally the book on computer programming, in which he discusses asymptotic representations and the O notation. Today in computer science, Big O notation is used to classify the time complexity of a given algorithm as to convey efficiency with respect to size. One would use this when trying to decide between two different algorithms. Consider two algorithms that are searching for a value in a sorted list. This one is going to start at index 0 and check if it is equal to the value. If it is not, it will increment the position and check again. This will continue to occur until the end of the list. If we were looking for a 7, we would compare 7 with 0, 2, 3, 5, and 7 before we found the match. That's 5 comparisons total. This one is using binary search, and we'll start at the middle index. If the element at our current index is equal to our search value, then we'll return the index. Otherwise, we check if our search value is larger than the array at the current index. If it is, we move the low bound to one above the current index, since the search value is larger. Otherwise, the high bound will get set to one below the current spot. When this loop repeats, the mid value will be halfway between the current high and low. If we were searching for 7 here, we would compare 7 with 5, then 8, then 7 itself, netting 3 comparisons. The time to do a binary search is much less, even in this small list. Although computers can compare values rather quickly, as a list grows, the time for each comparison is going to start adding up. This video demonstrates the binary search, with each comparison represented as a duet. One can imagine the additional length should they have performed a linear search. Even with that video at double speed, we can see the obvious inefficiency of modeling every sorting algorithm by choreographing a dance. As such, we use big O notation to describe these algorithms instead. In computer science, big O notation represents how much time it will take for an algorithm to process a list of a size n. The notation is discussed in terms of the arguments as to help in comparing different time complexities. As such, one could state merge sort is n log n. Although this is properly read and stated as merge sort grows at an order of n log n. Big O notation can be evaluated with a given n to find the worst case scenario of how long an algorithm will take to compute. As such, one can use big O to measure how well an operation will scale with respect to the amount of things it has to process increases. Big O can also be a tool in assessing how much memory an algorithm will use. Let's take a look at some of the notation that's used in this big O notation. Big O notation is only concerned with the worst case scenario, the most inconveniently unsorted list. There is also a notation for the average case scenario, big theta, and for the best case, big omega. If a function, f of n, is equal to the worst case, big O of g of n, then f grows at a rate that is greater than g. If f of n is equal to the best case, big omega, of g of n, then f grows at a rate that is less than g. And lastly, if f of n is equal to the average case, big theta, of g of n, then f and g grow at an equivalent rate. In big O notation, there are only four main rules guiding the operations that are used. Firstly, if loops are nested inside each other, their orders will be multiplied together. Second, if two loops come one after the other, the orders can be added together. However, when evaluating algorithms, as the size approaches infinity, we only use the largest term within the sum. For example, O of n plus O of n squared is approximately the same as just O of n squared for larger and larger values of n. Let's consider this if n is 100. O of n evaluates to 100, and O of n squared evaluates to 10,000. 10,000 plus 100 is 10,100. But if we only cared about the thousands place, this would just round to 10,000. This is the reason why we can say that the largest term is to be kept and why we drop off the other ones, since we're only worried about the largest time complexity with respect to the size of a list. Lastly, anytime a conditional appears in code, we evaluate that as a constant that will be executed on every pass. For example, if we are checking if the array at our index is greater than the value, we'll say that this has an order of 1 or that it is constant. Often when looking at new material, I find that when I view an example, it helps with my understanding. So let's start looking at a few. First, we have an algorithm that is constant. When the print function is executed, it prints the first value of the array, then returns. This will take as long as it takes the machine it is executed on to retrieve and print the value at the first address of the array. Next, we have our first example that utilizes the idea that nested loops get multiplied together. The innermost loop will start at 0, then run the same amount of times as our size. Therefore, this is O of n. Then, the outer loop will start at 0 and also run the amount of times as our size. And for every element in our array, the innermost loop will also run, resulting in an outermost loop executing an operation of order n times. Therefore, the whole expression has an order of n times n, or n squared. We can see this idea of multiplying nested loops extended here with n to the third. Since that j loop now has an additional loop inside of it that has an order of n, all three will be multiplied together to give us an order of n cubed. For n log n, we're going to look at heap sort. This for loop is the part that will sort the heap. Min heap is heapifying the unsorted heap after we add each element. If every element was added to the heap at the correct location, we would only have to run through this for loop n times to assign every value from array to sort it. However, since big O considers the worst case, we must assume at least one of these if statements is activating with each pass and forcing every new entry to be shuffled through the heap to the top. This process is similar to the binary search and will cause an order of log n. Since the two loops are within the same function, they will be multiplied together to give us n log n. When looking for an example of an algorithm that has an order of 2 to the n, a common problem that is evaluated is the Tower of Hanoi. Imagine you had 3 pegs sticking out of a block of wood. On the first peg is a tower of some size. Here, we show 3, with each block being smaller than the one below it. What order must the blocks be moved such that the same largest to smallest tower can be constructed on the final peg? Can the tower be any size and still be transferred? What we find is that one can always solve the Tower of Hanoi, and this recursive algorithm will do so with a time complexity of 2 to the n. Let's run through our example. Solve Hanoi will have its first run with the parameters 3, since we have 3 blocks, a, since the tower is currently on a, c, since that is the peg we want the tower to end on, and spare peg is b, since that's the title of our additional peg. 3 is greater than 1, so this will be false, and this one will be true, which will call back to the function. But this time, the spare and 2 pegs have been flipped. This runs again with 2, a, c, and b. 2 is greater than 1, so this is false, then true again. Now, solve Hanoi will run with 1, a, b, since that's our current spare peg, and c. This time, none of the if loops will activate, and we'll be told to move from A to C. So we move this red block over here to C. This function will now return to when we were in this if statement with the parameters 2, A, C, and B. The function prints out move from A to B. So we move the white block to the B peg. 2 is greater than 1, so this conditional is true, and solve Hanoi will be ran again with the parameters 1, C, B, and A. Since n is 1, none of the loops will activate, and we'll be told to move from C to B. So the red block gets moved on top of the white block. We now return briefly to the loop that had the parameters 2, A, C, B. We see there is no additional code to execute. Then we return to the first instance of the function with the parameters 3, A, B, and C. We are told to move from A to C, so we move the green block to C. 3 is greater than 1, so this loop will execute and run through 2 final instances of the function, for a total of 2 to the third, or 8 iterations. As such, this algorithm is 2 to the n. Our final example is n factorial. A math joke I find humorous is, if you scream 0 loud enough, it's equal to 1, since 0 factorial is equivalent to 1. Anyway, factorial is calculated by multiplying every number from 1 to n. So 4 factorial is 1 times 2, which is 2, times 3, which is 6, then times 4, which is 24. And if we ran this recursive function starting at 4, it will execute this for loop 4 times, which it will itself run the loop 3 times, which will run it 2 times, which will run it once, since n is getting decremented with every pass. And now we use the rule of nested loops and multiply the 1, 2, 3, and 4 together, resulting in a time complexity of 24. As such, this loop has an order of n factorial. So when we graph these, we can see how they grow over time. One can find graphs that color code good, okay, bad, horrible sections, but the goal of Big O is really to find the most practical algorithm for your task that has the lowest time complexity, such that as your algorithm handles more things, it will continue to run as efficiently as possible. We can see the ones we've looked over here: constant, binary search, linear search, heap sort, a nested for loop, the Hanoi tower, and n factorial. To graph these, we evaluate the order at n equals 10 and record the results. So at 10, we had the values 1, 3, 10, 30, 100, 1024, and 3,628,800, which is somewhere way up here. Likewise, at 100 things, we only have the constant log n and n remaining with 1, 7, and 100 respectively still on the graph. The rest of the algorithms had a time complexity that was so great it's not even shown on this chart where it goes up to 1,000. We wanted to provide a quick reference for big O notation that one could look back on if they wanted to quickly review the information as to work with big O more in the future. So this looks over different types of notation that are associated with big O and what different relations insinuate about the big O of those functions. Then here we have the 4 rules of operations with some handy examples. And here are the citations for the sources that we used for the presentation.